It's with great pleasure that I introduce today's seminar speaker, Dr. Laura Pan. She received her bachelor's degree from Beijing Normal University and her doctorate in physics from the Johns Hopkins University. She then became a research scientist at University of Maryland and at NIST in the Atomic and Molecular Optical Physics branch. Her interest in atmospheric science commenced at Hughes STX Corporation. She did retrievals with respect to TOMS and SBUV satellite experiments, and these are well known for making very accurate column ozone measurements. She then ventured to NCAR and ACD. Arriving here in 1992, she became involved with the MOPPET-CO satellite experiment group. And around this time, interest in the upper troposphere, lower stratosphere became quite important, both within ACD and other research institutions. She has been very effective in showing leadership in both bringing people from Europe here to visit ACD on a regular basis. There's a strong connection between ACD and Europe in this regard. And also for her activities in respect to using the Hyper aircraft. She's been instrumental in the success of the Hyper aircraft on a number of field missions, and today we will hear about UTLS physics and some of the applications of the Hyper aircraft.
Yeah. Thank you, Steve. My title page here highlights the observation studies of the global Tropopause. And this photo of under the title in the background is from the forward camera of the G5 aircraft during the recent experiment over the Western Pacific at a near 15-kilometer altitude above a solid cloud deck, and showing the division nicely of the lower stratosphere and upper troposphere. 2001 is important for me. I attended a Spark workshop on Tropopause. And during this workshop, this is the time I was doing my first paper in the topic. And I was deeply impressed by a small exchange, a conversation between two leading scientists in the field. One is a lead research scientist in atmospheric chemistry, the name of whom that everybody in ACD would know. So I won't need to mention that. And the other is a leading scientist in dynamics of the lower stratosphere. The exchange goes as such in my own words. The words is the chemist asked, we really need you to tell us where the tropopause is, how it's defined, so we can quantify how troposphere ozone budget is and the transport in the stratosphere is. And the dynamics said, we really need to know what is more useful among many of the definitions we have, so we can give you the best one. So with that, I realized how integral the dynamics and the physical structure of the UTLS is connect to the chemical study. So I call this a UTLS zoo. So you have many of the elements of chemical species and processes. You also have all the dynamic structures and the various boundaries and transition layers and such. Very complicated, but the point is, it's really important to study these two together. So with that, the general question really about the study is to start from the beginning. What is the tropopause, and why is it important? And what are the definitions of conceptual models that defines the tropopause, and how the definitions and models disagree or in agreement, and how they can be verified by observations. And also these observations ultimately should be used to improve global models. So the observations I'm going to be talking about is coming from large number of field campaigns, a lot of them from in situ aircraft observations. The important platform including NCAR GV, Hyper, and from various campaigns, in particular the START 08 and the START 05 campaign. We studied the tropopause intentionally, we targeted it. And also the recent contrast that contributed to the TTL study. Then also from the NASA Global Hawk experiment ATRACS that I'm involved with, and also from the DC-3 experiment, I show examples of DC-8 measurement, and also from the NASA ER-2 aircraft from as early as 1995 and all the way to Seekers last year. And I also use the ground-based balloon soundings and the satellite data, in particular ACD-led hurdles, and Calypso and Cosmic. So for the method of study, I want to emphasize how important it is when you design observation to have the chemical field and the dynamical field in mind. So you want to do the measurement such that you can line the two together. So in doing analysis, we want to aggregate the composition relative to dynamic boundaries, and also a very effective way of doing analysis to look at the things in the tracer space, the chemical tracer space, and the tracer-tracer correlations. So I want to highlight the G5 as a very effective platform for doing the studies. So this is a recent field campaign contrast over Western Pacific, how the chemical payload together with the microphysics is, to obtain a full suite of information for this study. I will talk about this at the end of the talk. So the line of discussion I'd like to go over is to start with a historical perspective, then go through the earlier work that really working on understanding the actual tropical tropopause. And that really is extended introduction to the later work, focus on the tropics, that is what is the TTL, how the tracers give a different perspective of TTL, and the lab-rated tropopause versus cold-pointed tropopause. Those are the ongoing studies. And I hope I have time to go over, to go beyond the large-scale view to talk about recent observations, present a mesoscale view of the tropopause, and finally, ongoing studies of convective transport in the tropics. So historically, tropopause is discovered after hundreds of soundings and in late 1800s. So very often, the final credit is attributed to the French scientist Bord, and in 1902, more than a century ago. And so the definition, the term of tropopause really comes from the original word is the troposphere is a turning and mixing sphere. So tropopause is when the turning and mixing stops. So that's the origin of the term. So I learned quite a lot, and very, very much enjoyed Klaus-Peter Honigke's review article in 1997. And giving the perspective, the early scientists rising up with the balloons and then became unconscious when the air became very thin. And that's how the tropopause is discovered. Now we know the textbook version of the tropopause. That is, in a static fashion, we know our atmosphere divided in many layers. These layers are defined very much associated with the temperature lapse rate change. And these temperature lapse rate change, and in the lowest level defines the separation between stratosphere and troposphere, are not just temperature changes. There are a lot of other changes that shows this boundary is physical. So this is a sounding launched from a news island around 2 degrees south less than a month ago. I just couldn't find a better data, so I apologize for Grant Wang for this private communication, without asking just to show it to you, because it's really an excellent figure. So what we're seeing here is a sounding that the G5 eventually did a collocated measurement for. That you have temperature in red curve, indicate where the tropopause is, and that this is a near zeroth order discontinuity at this point. At the same time, you have potential temperature, also near zeroth order discontinuity, showing unstable change to extremely stable. Then you have ozone in black, sharp increase at the same point. Then you have the humidity, water vapor, sharp decrease at this point. So this level really marks a very sharp, so tropopause can be extremely sharp, and it marks the sharp change physically and chemically in the atmosphere. So if we go beyond the static view to look at a dynamic view of the global tropopause, there are many known features highlighted here, that the tropical tropopause is higher and extratropical tropopause is lower. And above the tropopause, you have stratosphere, a lot of ozone, very little water vapor. And below, you have very little ozone, a lot of water vapor. So chemically, very different layers. Then you have the boundary very much marks the top of the cirrus cloud. So knowing that it marks a microphysical property change as well. And we know also the jet stream dynamics couples the upper troposphere and lower stratosphere. And because the sharp gradient, any change will be very important to increase the troposphere ozone and stratosphere water vapor. And it's the gradient of ozone and water vapor across the tropopause that is fundamentally connecting this region to the climate forcing. The radiative sensitivity make this region extremely important. Now that we also know not just the synoptical scale dynamics, also the convective system can penetrate the tropopause, inject water vapor into the stratosphere, and it can also wrap around the stratosphere and to bring stratosphere ozone into troposphere. So come to the definition. So what is this? From early sounding, the definition uses the temperature lapse rate, started the very first tropopause definition, and still the only definition that defines global tropopause. That is what we call the lapse rate, or the thermal definition of tropopause. That's defined by the lapse rate. In the troposphere, is 6 to 7 degrees per kilometer, when it decreases to 2 degrees per kilometer. And some other conditions lead to possibility of multiple tropopauses. And the multiple tropopauses typically always happen near the jet stream. And we call this a break. They also is discontinuous at this point. Okay. So this discontinued tropopause causes some discomfort. That is, we like to see a continued material surface that encloses the stratosphere air and separates the stratosphere and troposphere in an unambiguous fashion. Because of that idea, we start to look for a single continuous tropopause. The PV-defined tropopause become the dynamic tropopause. And except we don't know which PVU is the right number. And then most often, 2 PVU is being used. So what I'm showing here is a PV map on the 330K isentrope, and from a famous paper by Brian Hoskins, and showing how the bundled up 1 to 2 PVU heavy shaded enclose the stratosphere and separate the troposphere. So these two definitions, I call fundamentally created a dichotomy of the tropopause definition, because this is the classic view of lapse rate definition, and based on the static stability. And it shows the tropopause really is piecewise continuous and has breaks and can have multiple values. And then we have this dynamic PV defined tropopause as a continuous surface, and including the stability and also vorticity together. So we have these two tropopause. So I think for a long time, especially during the time of the workshop I attended, the common feeling is the PV is a better, more physical definition, because PV is a quasi-material conservative surface. And the most criticism for the thermal tropopause, the need for PV tropopause, is the break in the subtropics and the uncertainty of having multiple values. So the observations we did change this view. Okay. So I started talking about, so the breaks in the multiple tropopause is the key criticism for thermal tropopause. So what do we see in observation to show whether this secondary tropopause, whether of them are artifact of a bad definition or it's really physical? So we have satellite evidence, we have aircraft observations. I want to just show you the satellite result. The satellite result is from the Aura Hurdles satellite data, and with John Gilly was the PI in the room. And particular data we use is ozone. So on the left, we see on May 11th, 2007, hurdles along this orbit observed multiple layers structure of the ozone. The detailed analysis show this layer structure associated with the double tropopause, and the tropopause showed by the black dots. So when we do the dynamic analysis, what we found is, you have high ozone, low ozone, high ozone in the ozone structure. The same thing happened in the static stability analysis. You have stratospheric stability, troposphere stability. Then you have a layer of enhanced stability. On top of that is a layer of low stability. So if I look at this layer from the GFS model, in the map view, we see this extended layer of troposphere intruding on top of the first tropopause and created this structure. So more study following this shows this really is consequences of Rossby wave breaking on top of the jet core. And it happens very frequently, and we see that these layers are being mixed in as part of the, we define a new term called tropospheric intrusion. It's a troposphere air intruding into the stratosphere. Sorry. So what about near the jet stream when the PV and the thermal tropopause do not agree? And who is a better definition? So what does the chemical air mass look like that give us some hint? So this is also an early study. We used the G5 and the chemical measurement, and during the Start 08 campaign in 2008, we targeted a region that when thermal tropopause showed by yellow and the 2 PBU had a very significant separation. And this is in the region of blue, this is 250 millibar wind field shows where the jet stream is, where the 2 PBU and the 4 PBU surface are, and the blue is the G5 track. And we flew in such pattern to study in detail the separation. The separation is being analyzed in the tracer space. So the idea is as such, when you have a boundary like tropopause, the chemical tracer would call stratosphere tracer go through a sharp change, like we showed earlier. And the troposphere tracer shows another sharp change, a decrease. When you look at them in the tracer space, what you see is the stratosphere troposphere tracer form an L-shaped tracer relationship and a very compact relationship. And in the corner of L, very often you see mixing lines. And this turning of the L and the mixing behavior is what we use in the tracer space to define where the tropopause really is and the physical boundary really is. So using this method, this particular flight, the ozone and the carbon monoxide showed this L-shaped relationship. And with such a clarity, we can define where the stratosphere is, where the troposphere is, and we have a region that is a mixing of the two. Then we can compare that with the geometrical space. So we see that in geometrical space, this mixed layer is really in the region of strong separation of thermodynamic tropopause. So with this, we reconcile the concept of the two surfaces. One is a thermal, the other dynamical, and one layer, people call the extratropical transition layer, ExTL, and really is nicely reconciled by the tracer and tracer relationship. That is, when the tropopause is poorly defined, indicated by thermal and dynamic tropopause separation, and the two definitions together try to find in the region when the tropopause is broken, this is what happened. So the next one is when we have all this high resolution aircraft measurement, how do we use them in with global model? We have 1 second data here as an example from the recent flight, plot made by Andy Weinheimer, and the 1 second data showing a lot of structures, and in ozone, there's a purple and the flat track, and there's NOx and so on. So we do not expect our global chemistry climate model to reproduce the 1 second data as the way it is. So how do we use them to constrain models? So tracer correlation provides a nice tool to connect the two. So this is an example of ozone CO correlation you have just seen. And if we look at all the starred oil data in such a way, in the CO ozone space, and colored by potential temperature. So roughly you have red is the stratosphere, and the blue is the troposphere, and the yellow is the transition region of the jet stream. And this is the same picture in our global model WACOM. So we do not produce 1 second data in that kind of resolution, but the model reproduce the chemical structure and the characteristics of our atmosphere, so qualitatively, and there's a lot of things we can learn quantitatively. And similarly, we can look at other tracers of different origin and different lifetime using ozone and CO as their respective stratosphere and troposphere coordinate. When you look in such a way, and again, the starred and the WACOM, you can have a comparison that can be both qualitative and quantitative. So with this kind of method, we want to continue to use tracer correlation to study tropics. So tropical tropopause and the tropical transition layer is the next that I want to focus on. So tropics, I think many people in the room have heard TTL, just in case, I want to bring up the TTL as a newer subject, really started more than 10 years ago. And really is motivated by the concept of how we calculate, how we derive or quantify stratosphere water vapor. So stratosphere water vapor, if you calculate from the mean tropopause temperature, that is where in the tropics, water vapor get dehydrated into the stratosphere. If you use that, very often you do not get an accurate result of stratosphere water vapor. So the puzzle is, did the dehydration of the air mass rising in the tropics into the stratosphere happen preferably in some cold region? So this concept of TTL started from, I really like this paper from Houghton and Gettleman, really saying the dehydration of stratosphere really come the fact of in the TTL air arise not directly, but more horizontally and have a slow ascent while going through large areas horizontally and passing by the cold regions when they irreversibly get dehydrated as they go. So based on this concept, there was 10 years of intensive study. We have so many papers talking about TTL, and now at least 2 review articles. This is a Fuglitz-Taylor's 2009, and this is the more recent review paper from Randall and Jensen, both of them in the room. And now, with all this intensive study, what would a chemical tracer say about TTL? So this is the study I've been wanting to do for a long time, and eventually finally did it, and then I got in the campaign and I forgot to ask why the proofs never came. So it was accepted, and only recently found out it was in the crack of change of people working, and never received the proof. So anyway, so the work is about using ozone-water vapor relationship to characterize TTL. And then we use ozone water vapor instead of ozone COs because to cover the large range, right now we really don't have high resolution CO profiles. And then the question is, would we be able to apply the same method we did in actual tropics to study TTL? So it turns out that TTL has 2 subtly or not so subtly different definitions that have been largely ignored in the study. So the 2 definitions, one come from the definition of the idea of TTL should really be defined as tropical tropopause layer that is a boundary replacing the tropopause in its effect of dehydration. So to define that boundary, there are some arguments being made from a convection and energetic point of view. So in this specific Folkens paper, and define theta is the average quantity between 356K and 375K. And later on, Chang Fu wrote a nice paper using mass flux to find the level of lower boundary to be more close to 15 kilometers as a level of 0 net radiative heating. That is when the air mass after that started to ascend, rising up instead of descent. Then the upper level is being defined as the mass flux matches the Borer-Dobson mass flux. So this is a much higher TTL than originally we talked about. So the other definition is to define the tropical tropopause transition layer. That is the TTL really is a transition from the tropospheric control into stratospheric control. So this definition is specifically articulated by Andrew Gettleman and Piers Foster in the 2002 paper. In this definition, the lower level, the lower boundary is using as a proxy to characterize the base of the convective outflow. That is I think minimum lapse rate is misassigned. It should be a minimum stability or the maximum lapse rate, and which is 10 to 12 kilometer or 345 K. And the upper boundary is defined by the cold point where the stability changes sharply. So what is the tracer perspective? So the tracer perspective really says, and if this layer is a physical layer, it should be measurable. And the measurable, that means you can see the change in the chemical and the physical properties. So with this idea, we used a sounding data from Costa Rica. The sounding data has temperature, ozone, and water vapor from the ground all the way to near 30 kilometers. That gives us enough range to identify both background stratosphere, background troposphere, and the transition. And the method is very much similar to what we did before, but I want to start with the dynamic behavior. That is the behavior of the temperature in the tropics, which a lot of work devoted to that. Really, the basic understanding is really a radiative convective equilibrium created this temperature structure. And we know there's temperature minimum, we call the cold point. And we also know, based on the static stability, in this case, I use the theta lapse rate or theta derivative that defines the minimum static stability. And these two critical levels really separates the convective dominated region below and the radiative dominated region above. And the transition between the two is dynamically how our atmosphere transition from tropospheric dominated process to stratospheric dominated process. So what about the tracer structure? Now again, I have water vapor and ozone. And if I put them in a tracer space, I would be able to define a stratosphere branch and a troposphere branch. How did I do that? That's a level of detail I don't want to go into, so I hide them here just to tell you I actually did something. So, then the separation from the background is the transitional air mass that's in purple. And in the potential temperature space, right now they're between 340 and 380 K. In this specific case, they peaked at 360 K. So we call the mixed layer. It's really the transition. Okay, same concept as in the extratropics. So if I put this transitional air mass relative to the coordinate of our level of minimum stability, the one critical level, the other is the cold point tropopause as the other critical level. It is very clear this level, this layer, is largely controlled, lower bound by level of minimum stability and upper bound by cold point. So therefore, the tracer space reconciles the extratropics and the tropics, the transition layer, the level surface concept versus layer concept. So to summarize, that is, if we consider TTL as a transition layer, it is measurable. And the tracer correlation will show where the boundary is or the dominant process controls it is. And then this reconciliation is very nice to have to say chemically we know using the same method we can deal with the tropics and extratropics. However, what does it mean to the other definition? Okay, what I'm trying to say is because the other definitions of trying to define something different, that is a boundary that replaces the tropopause. So it's not something this particular method will invalidate. However, this method says And the other definition has at least the weakness of not being measurable because it did not use a local quantity. It has to use global average, so it's not instantaneous measurable. So the next part I want to move into is the definition of the tropical tropopause. So given that the TTL is important, it doesn't mean the tropopause itself is not, because it at least served as the upper bound of the TTL, right, as we just said. And we also know it serves as the upper boundary for a lot of physical properties, including the cloud. So in this study of the cloud top tropopause relationship, we found that the tropopause, I skipped one. The tropopause serves as the upper bound of majority of the cloud tops. So that is, clouds are mostly below the tropopause. This is what this work says globally and also in the tropics. So, but in the case study, however, we did find there are cases you have a cold point tropopause and a lapse-rate tropopause. It can be at different levels, separated as much as a kilometer or more. And in the single cases, we can co-locate a radio sound has high resolution and calypso data that give us cloud top. We do see both seem to have consequences to cloud top, but you do have clouds above the the lapse-rate tropopause, but below the cold point. So the question is how often, where these separation happen. So this leads to the next study of using the data to study lapse rate and the cold point tropopause. So this is 10 years ago, there is a such study done by Sadell et al. Using radio sound. When they use radio sound and did average over latitude, the result is you have lapse rate tropopause higher in the equator and get lower in the subtropics. Then you have cold point tropopause that is much more flat in general. It's half kilometer higher than lapse rate in the equator and about a kilometer higher in the subtropics. So now we have the global GPS data. We can afford to do a global study and see the latitude, longitude structure. So in this structure, we see a seasonal average, winter season, northern summer season. The lapse rate tropopause shows indeed mostly in the winter season you have higher tropopause near equator. So this color is 17 or higher. This is 15, it's 16 to 17, this is below 16. So we can see the decrease of tropopause, lapse rate tropopause toward subtropics. But when we look at the cold point, it's really interesting to see, not only is in general higher, but a lot of times you have higher cold point tropopause off equator, which is kind of hinted in this, but not as clear. So when we look at the separation, that is when we do the seasonal average distribution of the difference between the two, we found a really interesting structure. So this is, I want to focus on the northern winter case. So we see that you have black regions in general is a region of very little separation, that they too agree. And you have the regions, they have significant separations, and you have regions in subtropic, you have large separations. These separations are not zonally symmetric, it has a pattern. Okay. And so these are a lot more information than the zonal average that it can provide. So the question is, do we understand why they separate? When they separate, who is the better physical boundary? So this is a cross-section just to show typically what a cross-section looks like. And what is really interesting is, so what you're seeing here is a temperature structure. The temperature created by GPS profiles aggregated by 5 days or a week, and using a width of 10 degrees, and created the structure. So we see a layer of very cold air is responsible for the cold point that is in white. And we see the lapse rate tropopause drop down near the jet stream. And the separation is the largest near the jet stream. And the separation gets even larger as we go to extratropics. So this red dashed line hinted that the increased altitude of the cold point as latitude goes, and which they become irrelevant to tropopause. So, but even in the tropics, which is between the jets, and when and where the cold point is no longer meaningful, we know this no longer as a boundary, and it's really a question. So if the cold point is more physical for dehydration, and when and where it stops being meaningful, it's really the question. And we understand, so one of the new observational discovery is, it's not a discovery, but it's the point is, we understand why lapse rate decrease near the jet stream. That's just follow the thermal wind equation. You can find why this lapse rate should increase, should be like this. But we don't really understand why the cold point show a kidney shape that bending up in this particular segment of the atmosphere. So, so how do we do this? We like to find a better physical boundary. Again, try to use the chemical tracer measurement. Before we had any, based on some dynamical analysis, we had the following hypothesis. The hypothesis is when there's a large CPT, LRT, this two tropopause has a large separation on the seasonal time scale. It's behind that it really is the actual tropical driven dynamics is controlling, is contributing to the tropical region. So in such a region, the CPT is no longer a effective boundary because the motion is no longer upwelling. It's really more horizontal wave structure is causing that. So I won't show you the analysis we did that derived to this and just throw it up there. So the point is we really like to use observation to verify this. So this lead to one of the very recent campaigns I'm associated with Eric Jensen as a PI in the room, and using the NASA Global Hawk in this particular phase of deployment from Dryden Edwards and the plane, this unmanned aircraft Global Hawk went to deep tropics. So in this very first research flight, and we have many of the profiles the plane is making is a sampling. And this particular one highlighted by this dark black and passing through. We have many of these profiles is doing the same thing. I'm only showing you one example. So this is a rule, not exception, okay? So what we're seeing here is we sampled a cold point and a lapse rate, both tropopauses. And when we look at them in the ozone versus water vapor tracer space, you can see that the tracers did not really know about the CPT, and the tracers know the lapse rate is making the turn. So this is a clear evidence that under these conditions, that CPT can no longer be the physical boundary. So here comes the summary of the tropopause study. So really, it's hard to summarize. It's a lot of work to summarize. So the point I want to make is the chemical composition measurement unambiguously identify the tropopause as a physical boundary when and where it exists. So in this particular study, the largest, I think, transformative idea really is the thermal tropopause, as all that is very physical. And as much as the PV as a conservative quantity, it doesn't necessarily do a better job delineating what the stratosphere troposphere is. So when the two separates, usually is a good indication that we have an opening of transport pathway, and we need to look at the physical process behind them together. And in the tropics, the tracer-tracer correlation also help identify the transition layer and reconciles the actual tropical transition layer and tropical transition layer. The CPT, the question of cold point versus lapse rate is ongoing study. There's a lot to do. There's nothing as obvious as we like to be, and we want to do some more study. And the highlight I want to make is the tracer-tracer relationship not only help in the data analysis, also help connecting observations with the model. So it looks like I have plenty of time to go to some of the ongoing works to go beyond large scale. That is what we learned in a storm, in a mesoscale environment, how tropopause behave. So this is a nice observation from the recent DC3 experiment, which Mary was PI in the room. This particular observation is from the NASA DC-8. And on this day of May 30th of 2012, and the DC-8, after some sampling of downwind studies and returning to Salina, Kansas, and this is in Missouri and Kansas, and encountered this very large convective, mesoscale convective systems. It's a typical of called leading line trailing stratiform, LLTS, MCS. I'm sure everybody in MQ or everybody had taken dynamical meteorology knows this very clearly as a classic system. And when we go through this classic system, with the DC-8 LiDAR, up-looking, down-looking ozone provided this cross-section. So in this cross-section, we have ozone, and the red color indicating very high ozone is a stratospheric, and the yellowish is a transitional, and the bluish is a troposphere. So we see this very striking signature at the edge of the cloud defined by the depolarization ratio, that the stratosphere at the edge of the MCS is wrapping in and going all the way to as low as 8 kilometers. And leading to the storm, we also see, as the plane, this is the direction of the plane as the direction of the curtain. Leading to that, we see enhanced ozone showed up in the filamentary structure and in the downsloping, and we call it shedding. So the wrapping and the shedding of the stratosphere ozone. And potentially, this is a sign that it's some processes we have not looked at before and is not considered in the ozone budget before, that the storms actually is a significant contributors to stratosphere to troposphere transport of ozone. And it also says a lot of things about the tropopause. So this is the classic schematics for this leading line trailing stratiform. It's made by Bob Halsey and colleagues in 1989. And now that based on the tracer measurement, we provide unique additional perspective of what the storm is really doing beyond the rain and the ice. That is, a storm actually is breaking the tropopause, and these injections are having additional different studies, but then we know at the edge of the cloud. And this is also not a single case. We have seen other things. So we see the violence of the storm is breaking the tropopause and bringing the air mass around. So this brings to this last new project. We are using the G5 to study the TTL, or the tropical convection, that just ended. We just all came back from Guam. And this is studying the Western Pacific convective transport active species in the tropics. And I owe my co-investigators to lead the project, and a large number of ACD people participated, many are in the room. And we did 16 research flights, and what's showing here is the flight track, and based from Guam, and indicating the long-range capability and of the aircraft allowed us to study from ice south of 20 south and to 40 north. And the southernmost we've seen is by the Great Barrier Reef of Australia. And we also go from as high as 48,000 feet, and the highest we've gotten to 15.2 kilometer GPS altitude, and as low as 300 feet above the sea level. And we worked in collaboration with the two other aircrafts, two other projects. This is the ATRAX Global Hawk project. They help connecting upper troposphere into lower stratosphere. And this is the BAE 146. I forgot the label. I thought I over-prepared this talk, but I missed the label of BAE 146 from the CAST project, and studied the boundary layer. It's a nice group photos. Everybody's happy in the open house day. A lot of local people came to see our plane.
All those people didn't fly in the plane, so how many people could fly in the plane and somebody's flight enough to get out that high?
It's not about the lightness, it's about the seas.
Okay.
So But anyway, so these are a large group of people participated, not everybody. There are a lot of people participated who did not make in this photo, but nevertheless, we had a good time. So just to showcase one simple example, and this is the day 3 aircraft happily flew together. So we have the global hawk track and the large range, and we have BAE coming out for the second, they're very short range, for the second time of the day. Then we have G5, and we repeatedly targeted this convection. So this is satellite IR images and showing the 40,000 feet-ish in blue and above that in red, and some active regions above 50,000 feet. So we tried 3 times to go in there, get a lot of really nice sampling. And Jim Brash is in the room in the back and played an important role in doing forecast and nowcast, helped the plane, and also a lot of EOL people and our pilot. And here is when we really got in there. See what we got here. We got unambiguous signature from our chemical tracer measurement. So this is from Toga Group, and Eric Apel is the PI, and Dan Reamer is on the plane for this one, and got really excited when we have, this is updraft 13 meters per second, and this you see a large signature of formaldehyde, very short-lived species, usually only see it in the boundary layer. And Becky, over the night, made this figure. So the next morning after flight, everybody enjoyed seeing how well we did in the field. So again, this is preliminary data. So with that, I'll give some concluding thoughts. That is how important it is to have dynamical and a chemical process study together in UTLS. And that the composition observations, how much they can also tell about the meteorology, about the dynamic systems, and how important we should value the observations. So I had a hard time making this figure because I can't fit everybody I collaborate with in this page. So this really I ironed on the left side. So I want to show how important is Bill Randall, Brian Riley, and Sue Schaufler worked with me. We created UTLS initiative that enabled most of these studies. And many of the people along the road helped me with the learning campaign and the modeling and so on. Then I also want to show the appreciation of the postdocs I worked with during the time. They really go in to expand the concept and the impact of these concepts of the tropopause and convective transport. And also the associated scientists, they helped me, and many of them made the figures I showed today. And the science teams of people, there are many of them in the room that did this measurement, and the last not least, that provided the foundation of this analysis over the years. And many people, I don't know how to list people's names. So, thank you. If people have questions, I can just, hey, Brian. I will repeat the question if the people complain online.
It's being recorded, so really.
Yeah, I will repeat. It's okay. I will repeat. Yeah.
I just wondered if any of these big models at NCAR predict changes in the tropopause, whichever one you want to find, with global change.
So Brian's question is, any of the big models at NCAR predict change in the global tropopause?
Especially the tropical one.
Especially, I think this is not just NCAR model question. This really is a global model question. So there are a lot of studies that using analysis and to see the widening of the tropics. And Bill in particular did the work, and there are many other people doing the work. So there's, in general, the analysis shows consensus there's a widening of the tropics. So because the tropical tropopause is higher, the widening of the tropics indicated the higher average tropopause height globally. I will just stop there. I think a lot of other people, Andrew is here, and is working a lot more on the trends and the CCM Bell project, and there's tropical tropopause evaluation in particular compares how model worked compared with observation. Yeah, Andrew want to add to it?
No, I'm talking about that later, Brian. Another question. You showed, like in the extratropics, the double tropopause structures and the separation was very much a horizontal transport issue.
Mm-hmm.
How much do you think does that come into play also in the tropics, in the separation between the lapse rate and the cold point tropopause?
So this break and this wave breaking is really a two-way transport. So in the recent, even during the contrast experiment, we see a large intrusion from the high latitude stratosphere getting the tropics also from the other side of the same process. So this raspberry wave breaking above the jet and how that transport in a symmetric poleward, equatorward, and a bilateral fashion is a topic of Cameron Holmeyer's PhD dissertation. He wrote a nice paper on that. Yeah. Eric.
Yeah, I can holler. So you showed the very interesting the smiley face structure of the tropopause versus latitude and tropics and subtropics. You said we really don't understand that. Is there any hypotheses?
That's a good question. I didn't know we didn't understand that. So when I saw that, I thought it really interesting. I visited a few theorists, and Lorenzo Pavani and Stefan Fugli-Steller among a few. And they both thought it was really interesting, and it's also, there are some indications of the dry adiabatic, what is the GFDL model has some hint to it. So I think this will be a nice future study. Once this paper get out, there will be theories that should be getting on it to understand why. Yeah. Any other questions? And Roy, please.
Near the top of the MCSs, Bob Sharman.
Yeah, I think this. Yeah.
Bob Sharman has shown some interesting results near the top of MCSs where they look like boundary layer rolls, and I was wondering if those play any role in the transport of ozone in that region.
I'm sure the turbulence around the MCS plays an important role in this. How specifically different kind of process we have to look into. I know Bob and Todd Lane has a recent paper just came out talk about the turbulence near MCS.
And I was wondering if you made any connections to the turbulence because there's now in situ turbulence measurements with aircraft near the tropopause, and those may be indicators of mixing.
So these are the things we have to look into more. At this point, most of the work from the, with the exception of Bob and looking at the aviation safety, most of the work from dynamical meteorology focus on in-cloud. So at the beginning, when we looked into the previous work, most people look in the in-cloud. So outside the cloud seems to be not as much of an interest of the meteorology study. So, but again, we should follow up the turbulent study. But in general, I'm sure the mesoscale process turbulent is important. But overall, I think the key point I want to make is the storm is like a bomb. You have a process of, the general balance requires subsidence outside the cloud. We just never thought that these subsidence, other than raining, also has such a significant chemical consequences. Yeah.
Thank you.
I was going to make a comment similar to Roy, and you often see pileus over the tops of deep convection overshooting tops, and this is a stable layer, so you probably get the propagation of gravity waves, and I wonder how that would influence the structure, especially in the tropics.
Yeah, these overshooting and how the convection and the gravity wave is a lot of focus study of various groups, and Todd Lane did a lot of work on that, and Cameron Holmeyer recently also did a lot of work and had paper modeling the using WRF and so on. So it's really part of the ongoing study. Yeah, definitely. Yeah. Any other questions? Okay. Yeah.